that we talked about? Should I go through and solve these real quickly just to get you set up? Heard some yeses and some nos. I think the yeses have it. So let's go through and work through this process. What is the molarity of a solution containing 24 grams of sodium hydroxide and 0.1 liters of solution? So what we're asking for is molarity. As we've talked about this entire semester, what you need to do is focus on the unit. What are our units for molarity? Moles over liters. So if we're going to go through and do this, what we need to do is figure out the moles of sodium hydroxide in the liters of our solution. Okay? So the approach that we talked about already, we're going to take a slight variance from that and look at another way to approach this. So to do this calculation, I need to know what number shows up in front of x and what numbers show up in front of y to do this calculation. Do I know either of those numbers?
Yes.
Okay, the question tells me that I have 0.100 liters of the solution. So I know the number and the unit matches, so I don't even have to do a unit conversion on milliliters to liters or deciliters to liters. Okay? So I know that y value. Do I know the x value? No. So I need to solve for that x. The number for our x, or our unit, is moles of sodium hydroxide. What do I know about either moles or sodium hydroxide? So we know a molar mass. Okay, we could figure out the molar mass by doing what? Adding up our molar masses from our periodic table. It's not officially atomic masses because that's AMUs. We're talking about grams per mole here. So sodium is
22.99.
Stupid sig figs, but okay. 22.99 grams per mole. Oxygen
16.00.
hydrogen. And I would love to say that I picked a species that came out to a perfect round number, but I did not intentionally do that. What do we end up with? Officially 40.0 grams per mole. Let's convert that to something a little bit more useful. This is 40.0 grams of sodium hydroxide per 1 mole of sodium hydroxide. Yes? So that now gives me a conversion between grams and moles. Okay, so we could start to slide that into our equation if we so desired. Okay. Do we so desire? No. No. Okay, that's fine. So we've got some information there. We just went through and did a whole bunch of calculation, but at this point, we're not doing anything with it. What other information do we have about either the moles or sodium hydroxide? And I don't quite want to hear amount, but I know where you're going with on that. It's not an amount, it's the mass of our sodium hydroxide. We start with 24.0 grams of sodium hydroxide. Are grams equal to moles? No. So I have to do a conversion. I want grams of sodium hydroxide on the bottom. Why? So it cancels the grams of sodium hydroxide I start with. What do I want in my numerator? Moles of sodium hydroxide. Why? That's what I want my answer. So ideally I have this direct conversion between grams and moles. Do I have a direct conversion between grams and moles of the same substance? Yes. What is that conversion factor known as? The molar mass. Where is that conversion factor found? Periodic table. By adding up all the molar masses of each of our elements, and that gets us to 40 grams of sodium hydroxide per 1 mole of sodium hydroxide. Which now brings up the question, where do we put the 40 and the 1? So someone on the far side of the classroom, I believe, said this the way I wanted it. The 40 goes in front of the grams. It has nothing to do with top and bottom. It has to do with the unit. Okay? What shows up in front of our moles? 1. When we now go through and do our conversion, we end up with the number of moles of our sodium hydroxide, which was X. How do we solve for molarity? X over Y. We don't even need a conversion factor. Remember, our molarity, we said, was moles of sodium hydroxide divided by liters of solution. We know what the liters are. We now know what the moles are. All we have to do is divide those two numbers. So it's now just a question of punching it into the calculator and we get our answer. Kind of, sort of?
Yeah.
Questions? Do we need to work through this one? I actually heard mainly no's there. Interesting. Yeah, I know, we did it. That's why I'm asking. We'll see why I'm asking in a second here. Confident with it? No. Okay. One very confident no. So let's go ahead and work with it. My pen works. There it goes. How many grams of potassium dichromate are in 125 milliliters of a 0.15 molar solution of potassium dichromate? What do we want? What's our answer need to be? Grams, thank you for the of potassium dichromate. What information do we start with? Okay, officially of our solution. Okay. Is the milliliters of solution equal to grams of potassium dichromate? No. So what do we need to do? Conversion. Okay. So ideally, we'd do milliliters of solution and grams of potassium dichromate. Do we have a conversion factor between grams and milliliters? No. So what can I convert the milliliters to? Liters. Is this necessarily right? No, but it's something I can convert to. Okay? And we'll notice if we look back to what our molarity was moles per liter. So we're now actually getting our unit into something that we also have already given. What is our conversion factor? 10 to the minus 3 liters is 1 milliliter. So our power of 10 always affects our base unit. I now have liters of solution, and I want grams of potassium dichromate. Do I have a conversion factor between that? No. But what's this 0.15 molar thing? What is that? 0.150 moles of our potassium chromate per 1 liter of our solution. Okay. So I may not be able to get to grams, but I do have a way to convert liters into moles using that conversion factor. What number shows up in front of moles? 0.150 over 1 liter. What unit are we now in? Careful, and just because you're up front, you're going to get called out on it. What units are we in?
Not moles.
Not moles per liter, true. Milliliters cancel, liters cancel. We have just moles. The answer I wanted was grams of K2Cr2O7, our dichromate. Is there a conversion factor between grams and moles? Where's that conversion factor found? In the periodic table, which 294.2. Are you serious? I actually remember the number right. 294.2 grams of potassium dichromate per 1 mole of potassium dichromate. Our mole units cancel. We'd have grams of potassium dichromate. There's our answer. All we got to do now is push it into the calculator. and we'd have our final answer. Okay. So it's a question of knowing where the individual conversion factors come from. Okay. When we're dealing with mass and moles, periodic table. When you're dealing with, moles and volume, that one actually gets a little bit trickier. At this point, we would say moles and volume is only related through molarity, okay, our solution concentration. Okay, if we're doing numbers of atoms or numbers of molecules and moles, we need to use numbers of atoms and moles. Not the periodic table. What was that? It's Avogadro's number. Okay, that big nasty number that we talk about and say, oh, it's the greatest thing on the planet that we never use. Okay? So we have to be aware of where we find each of these conversion factors. A lot of them are found on the periodic table. How do I convert one substance to a different substance? It's a trickier question. Let me rephrase it. How do I convert a reactant to a product? Through a balanced reaction equation. Okay, so all of this information is slowly built up, and we're just now processing and doing all of these conversion factors. There's very little chemistry actually involved in a lot of this. Okay, for the most part, it's just organization of the units and canceling units. That's it. Okay. Questions? No. I like the answer. Appreciate that. So, application of molarity. So I know this is kind of small because we're going to write a whole bunch of this out. For those of you that have looked at the homework, this may look relevant, so it might be an important thing to take notes on, just for future reference. A chemist needs to determine the concentration of a solution of nitric acid. She puts 745 milliliters of the acid in a flask with an indicator. We'll talk about what the indicator does in a little bit. She then slowly adds 0.2 molar of barium hydroxide to the flask until the solution changes color. Okay. Our indicator is what's changing color. So all that indicator is doing is telling us, whoop, we're now at the equivalence point. The equivalence point is now saying that the amount of base present is equal to the amount of acid present. Okay, so the mole amounts are equal to each other. She notes that 165 milliliters of barium hydroxide was needed to reach this point. What was the molarity of the nitric acid solution? So, those of you wanting practice with nomenclature, here it was. First thing we got to do is go through and come up with an equation. We're taking nitric acid. The acid implies that we have a hydrogen bound to nitrate, and we can say our spase is aqueous. Okay, I'm not a big phase person, so I wouldn't take off points for that, but officially it's there. Plus, what are we now reacting it with? Barium hydroxide. So there's our formula for barium and our formula for hydroxide. The charge on barium is a +2, charge on hydroxide is a -1. If we left it as is, the charge does not balance out to form a neutral compound. We have to have 2 hydroxides. But then it looks like 2 hydrogens. So I have to include the parentheses around that. We now set this up to do a reaction. Okay, because all we asked for was the reaction equation at this point. What type of reaction is this?
Neutralization.
There are 2 answers. The most correct one is neutralization. The other answer is double replacement. So we go through and we exchange our ions. We end up with barium with our nitrate. And we end up with hydrogen with our hydroxide. Okay, we'll address that parenthesis in a second. What is the charge on barium?
2.
+2. Charge on nitrate. Does our formula balance? No, so what do we need? I need to put a 2 next to the nitrate in our parentheses. Hydrogen has a charge of +1. Hydroxide -1. So that formula balances, which means I now need to get rid of the parentheses, because the parentheses are not necessary. Okay. We now have our formula, our products predicted and those formulas balanced. So now what do? Balance the whole equation. Going through and balancing that, we should end up with a 2 here, which I meant to do in a different color. Give me a second. 2 there, and a 2 here. Everything should be balanced. Okay? You should be able to balance at that speed. If you are not able to balance at that speed yet, you need more practice. Go back to the textbook and work all of their balancing questions. The next part of the question on the quiz was provide the information underneath each of these. Right, we are told that we have 745 milliliters of acid. We are also told that we have 0.200 molar barium hydroxide, and we have 165 milliliters of barium hydroxide. The question asks for what? The molarity of our nitric acid. How do we solve for molarity? This, by the way, is now not on the quiz. Now we're actually answering the question that was asked. Okay. How do we calculate molarity? The moles of NaOH over liters of NaOH. What's your statement? Okay, let's address that real quickly here. So if we go back to the X and Y system. So what you just suggested here is that we change the 165 milliliters into liters. Why?
Because there's not milliliters and molar,
Okay, good. I agree with that statement, and that makes me feel better because I thought you were going to make a different mistake. Okay, so I'm glad you didn't make that mistake. Okay, so that's awesome. So we're looking at our units. Our molarity, again, useless. We should convert that to moles over liters. Okay. We have milliliters and we have liters. The units don't match up, so one of the very first things we can do is make sure that our units match up better. That means either converting our liters into milliliters or converting our milliliters into liters. Okay. Either way you want to approach it is up to you. As far as writing your workout for that, I would highly recommend it. Okay. A lot of people insist that they can do that conversion in their head and they don't need to show any work, and then they get the question wrong because they did the conversion wrong. So write the conversion out, please. You had a question?
I'm just confused. Why are we looking at NaOH? Should it be HNO3?
Oh, I see what you're saying. Sorry. You're right. That should be the solution.
Okay.
Okay. Thank you. I didn't even see that. Okay. So we need the moles of HNO3. We need the liters of our solution. Do we know the liters of our HNO3 solution? We know the milliliters. So we could try and convert to solve for Y liters of solution by taking our milliliters, which was 745 milliliters, and converting that into liters, which then says 10 to the minus 3, 1 milliliter. We now have our liters. Y equals 0.745 liters, assuming I did the conversion right. Now what do we do? What are we still missing to solve for molarity? Close. It's not just moles. Moles of nitric acid. We need to know the moles of nitric acid. This is where the question is going to rely on the balanced equation. Okay. The whole setup was that we took that volume of barium hydroxide, 165 milliliters, with that concentration, and we mixed it to react all of our nitric acid. Okay. So what we are trying to do is take this sequence of numbers from our barium hydroxide, and we're now going to convert that into, stuffs is technically correct, but we can get a little more accurate than that, moles of nitric acid. Which I may run out of space, but I'm going to attempt to cram it in here. We are starting with 165 milliliters of our barium hydroxide. Since I am going to run out of space, I'm going to write Ba there. I need to convert that into moles of nitric acid. Do I have a direct conversion? No. What might be a nice first step? Milliliters to liters. Okay, we're now in liters of barium hydroxide. What can I do now? Can I convert the liters of barium hydroxide to anything? I can convert it to moles using molarity. So liters of barium hydroxide, moles of our barium hydroxide. We know 1 and it's not a 0 in there, is there? Okay. We now run into a problem. I'm now in units of moles of barium, and I want moles of the nitric acid, which I'm just going to abbreviate N capital A. Where do I find that conversion factor? From the balanced equation. The balanced equation allows me to convert a reactant into a product. It also allows me to convert one reactant to another reactant. What number needs to show up in front of the moles of nitric acid in my conversion?
2.
Why 2?
Because that's how many.
Go up to the balanced equation. What number shows up in front of nitric acid? 2. What number needs to show up in front of moles of barium? 1. We now know the moles of nitric acid. What were we solving for? Moles of nitric acid. Ultimately, our goal was to get to molarity of nitric acid. To solve for the molarity of nitric acid, what do you need? The moles of nitric acid, we just solved for it, and the liters of nitric acid, which we already have. What do? Divide those two numbers, you now have your answer. Okay. Just like all of our other conversion factors that we've talked about in Chapter 8 and earlier, what we now need to do is string this back to a balanced equation to allow us to convert that substance. We can now solve for the molarity of an unknown solution. Is this an important thing to do? It usually is. Right? It's also usually with a more complex example, which I decided to not evaluate in this case. Could we potentially let's not approximate, those numbers are too ugly for me. Okay. Questions? Sorry, yes?
So do we have to do anything with the milliliters of the acid?
To solve for the molarity of our nitric acid, what do we need to do? Sorry, you already asked the question. It's already out there. You can't take it back. What do we do? Take our X moles of nitric acid, which we solved for from here, and we will divide that by our Y liters of our nitric acid, which we got over here. Okay. Questions? Okay. So, what type of reaction was this? Neutralization. It was a neutralization because we neutralized an acid. Acids tend to have kind of a rich and glorious history because their chemistry was fun, usually because it caused people lots of pain. Okay? So what we end up now looking at is our definitions of acids and bases, and we'll look at a little bit of their history and how we manipulate them.
Is there any acid that doesn't have hydrogen in it?
Sort of. We'll get to that question in a second. So acids and bases. Okay, the main reason we go through and classify them according to acids is that their chemistry is now drastically different from most other compounds. So that last one, H2SO4 aqueous, is now sulfuric acid. Okay, we're signifying it in the name because acids tend to be dangerous. They tend to burn us. So what we had to do is come up with a new name to allow us to signify and see that. So what is the characteristic that each of these things have? Yes?
If it can be aqueous, does that mean there's a solid form of it?
Not necessarily. So initially what happened is that observationalists noticed certain things. So a lot of chemistry gets names for people. So you move into OChem, we name for reaction after somebody because they observed something. They didn't explain it. They didn't understand how or why it worked, but they saw it. And since they were the first ones to see it, they got their name associated with it. Kind of a crappy system for science, because then what do you guys end up having to do? Memorize all these dead people's names in association with their reactions, as opposed to understanding the chemistry. But that observation came back to a couple different things. We noticed for our acids, they're almost always sour tasting and they tend to be sticky feeling. I'm not recommending that you taste any strong acids.
It's your skin sticking to each other.
Yes, people taste acids. And I would actually argue that a lot of you have tasted acid before.
Citric acid.
Like citric acid, like your sodas, okay? Like Gatorade. All of those have acids in them.
But nobody's going to be tasting sulfuric acid.
Theoretically, no one should be tasting sulfuric acid. But they could potentially have gone through and done that test. Scientists were pretty messed up in the past, and I'm not going to say they did the nicest things, but more than likely what they did is they made some slave taste it. Right. Yeah, scientists are cool that way. They also found there's a category of chemicals that are very bitter tasting, and they have a very slippery feeling associated with them. And what we noticed is that when we took those two compounds and we put them near each other, what happened? Sometimes you saw a fizzing, but more commonly what you saw was a drastic increase in heat. Okay, the solution got very, very hot because the type of reaction that they did, a neutralization. We mixed these two species and they neutralized each other.
Like the thing with copper.
Right.
Or you have.
We'll talk about, I know what you're talking about. No, it's not that. Okay. So with these two categories, they went through and wanted to label them as something slightly different so that we could identify them later. Okay. These later got called your acids and your bases. Okay. That slippery feeling that you're feeling is because the base is reacting with the fat in your skin cells and turning it into soap. Well, that's why you get that nice slippery feeling, because you're actually cannibalizing your skin, okay, and turning it into soap. Nice little process. Okay. So acids we've already seen before. How do we know that this first species was an acid? What did we look for? We needed an H, and in particular, we needed an H in front. One of the extra rules that we made you go through and memorize was that you saw this aqueous. Why? Most acids, or at least when acids were initially discovered back by Arrhenius, what he ended up looking at was the change in concentration of hydrogen ion. What he found is that when acids were dissolved in water, the concentration of H+, the hydrogen ion, went up. And he noticed that he went through, when he dissolved bases, the concentration of hydroxide went up. So that's how he defined acids and bases. Fun little difference about acids and bases is then that this definition only applies to hydrogen ions and only applies to hydroxide ions. Problem with that definition, it is very, very narrow. And because we're dissolving in water, there's where our aqueous comes from. So I tend to be the ever optimistic person and call this definition ultimately pretty freaking useless. Though it is the basis for a lot of what we end up doing in 152. The second definition came along by Bronsted and Lowry, expanded the definition ever so slightly. So what they that's probably a bad idea to talk back there. Let's try that again. What they evaluated was again looking at the transfer of a hydrogen ion, but they noticed that some species don't give up hydroxide, but will still accept the hydrogen ion. Okay. So if we look at the overall reaction that we've got up here, what we are taking from our HCl is ultimately the H+. What we are taking from our NaOH is OH-. When they react, they form H2O. Okay. So in our Arrhenius definition, it's just here's H+, here's OH-. Too narrow. So what Bronsted-Lowry went through and did said, well, H+ is still really important. Okay, so we're going to keep the definition of an acid being H+. But we need to tweak the base definition. Okay, and what they tweaked is instead of looking at it as the existence of hydroxide, they changed it to a hydrogen ion acceptor. So all they're really saying is that the hydrogen ion is the most important aspect of what makes acids and bases exist. What's happening between those two species is that one species gives up H+, the other one accepts it into the structure. So if we take a look at HCl and that reaction, what happened to it? If we look at the HCl structure, it becomes NaCl. It gave up a hydrogen. What happened to the NaOH structure? So we could say it gave up the Na, and we'll talk about that in a second. What were you going to say? It took a hydrogen. Okay. So what we're looking at is how does the reaction change? You'll notice that we skipped over the Cl and we skipped over the Na. Why?
They don't matter.
Why do they not matter? That is true.
That's not what you're looking at.
So they are not hydrogen. Kind of made sense, yeah. Okay, there's another reason. There it is. Sodium ion compounds all dissolve in water, meaning the sodium becomes a spectator ion. The chloride ion, in this case, when we bond it up with that sodium, also dissolves in water, and we have yet another spectator ion. They are not involved in the overall chemistry, so I don't care about them. Okay? Sort of. So we can kind of push them aside, and we look at where our bonds are changing. Why do we really push that? What type of bond do we have between sodium and chloride? Ionic. What kind of bond do we have between sodium and hydroxide? Sodium and hydroxide is ionic. What kind of bond do we have between hydrogen and OH? Polar covalent. We're making a stronger bond in our water molecule. So we are focusing our definition on the formation of the stronger bond. That's where these definitions are coming from. Okay? So we got two examples up here. HSO3- plus water, and SO3- 2 plus H3O+. So what we're going to look at here are our conjugate partners. So in this first case, I'm going to tell you that HSO3- is going to act as, any guesses? What do you mean a donor? Hydrogen ion donor. Can it also act as a base? Yes, but I'm going to tell you it acts as an acid. If it acts as an acid under these conditions, what does that mean the water has to act as? A base. Okay. What do acids do?
Destroy bases.
Nope. Our definition of an acid? That's not the definition.
Corrosive. Donates the hydrogen ion.
Donates hydrogen ion.
Taste gross.
So what would the product be? What would SO3- look like if it donates H+? What would be left? SO3, Y-2. Not just H left, H plus left. It lost a positive charge. So what we're trying to do is evaluate what those definitions mean and start to predict what happens to the structure. Our base must add H+. The result that comes out of this, I now can predict those two products. Okay. What happens with SO3 minus 2? Can it act as an acid? Why not? No hydrogen, so it can't act as an acid, which means it will act as a base, which means H3O plus acts as an acid. What happens? The acid needs to lose H plus. What happens to H3O plus if it loses H plus? Becomes? Get rid of H plus from H3O plus. What are you removing? How many hydrogens should be there? 2, and our oxygen. What should its charge be? So this one's actually, I would argue, a little bit easier. It's losing what? It's losing H and it's losing plus. So what did we do? We got rid of one H and made that a 2. What do we have to get rid of also? The positive. What do we have? Neutral. We have H2O. Okay. So you're looking at the balance of those charges again. What happens to the SO3 minus 2? It must accept a hydrogen. So we're now going to have HSO3 minus. Why did I not put 2 hydrogens on it? Because all I'm asking you to do in this case is a single transfer of a hydrogen. So this is slightly different from reactions we've done in the past. Because in the past, what would the charge be on all of my products? Neutral. Can't have neutral products when we're looking at our acid-base reactions. Okay? Our overall charge will pick up, our overall systems will pick up charge. The next part of this is this phrase known as conjugate partners. Okay? What we are linking is the most similar species across the reaction. Across the reaction, what is most similar to SO3 minus 2? Is it HSO3 minus or H2O? HSO3 minus. What does that mean? SO3 minus 2 and HSO3 minus are conjugate partners. That's all we're referencing. You'll notice that it's not just saying it's a conjugate partner. I'm saying it's a conjugate acid. Why is it labeled as a conjugate acid? Because it became what? How did it become an acid? How do you know that that species is an acid? We could see that it gained a hydrogen. The other thing we might look at, you'll notice that our reaction arrow is not our standard reaction arrow. What's different about it? It is bidirectional. I can take HSO3 minus and I can convert it to SO3 minus 2. How do I do that reverse reaction? I have to take a hydrogen away from HSO3 minus. If HSO3 minus loses a hydrogen to become SO3 minus 2, what did it act as?
Does this happen continuously, like back and forth?
Yes. An acid. So it is a conjugate acid. Okay. As far as all chemistry goes, all chemistry does this back and forth. This is a very interesting, difficult concept known as equilibrium. Okay. So our double arrow is just saying our reactions can go both forwards and backwards, which means all of the calculations that you've run through can now be going either direction. Okay? So we're looking at a balance of our products and reactants. Almost all of 152 is dealing on equilibrium and all of the examples that come out of it. You're looking at single problems taking an advanced person at least 10 to 15 minutes to solve. Okay? So the calculations involved in that section involving equilibrium are difficult to process. One of the things that comes out of this is this principle known as LeChatlier's principle. Okay? Presumably a French guy. Okay? The reactions will do whatever it takes to achieve equilibrium. Okay? What it means to be at equilibrium is the rate of your forward reaction is the same as the rate as the reverse. Not that you have equal reactants and products, but that the rates of those reactions are equivalent. Okay? So what does this mean for us as far as interpretation? Okay? So we've got 2 ways that we can look at this. We can either look at it as a seesaw or 2 divided chambers with some liquids. All right, so let's take a look at the seesaw. Equilibrium is saying that I am balanced. So if I put my equilibrium triangle right there, I could put a blue box here. What would I draw for my red box on the right side? If we assume they're all the same size, or same mass, same density, all that. I should draw the exact same size red box. That's supposed to be exactly the same size. Close enough. Okay. What happens if my equilibrium instead is established here? Okay. I am currently not at equilibrium. The seesaw is unbalanced. What does the reaction do to balance? So we could try moving the red block. I didn't think of that one. You can't move them. Put more blue boxes on the blue box side. What's that going to do? That will now balance out according to your physics and leverage so that we now achieve that flat line again. We are now at equilibrium. Here's LeChatlier's principle. I mess with the reaction. I remove that blue box. What happens? The red box is going to fall. Okay? The reaction must re-achieve equilibrium. How can it do that?
Shaving off some stuff from the red box.
We can't add more blue box because we're in a closed system. We can't just add more of the reactant to balance it out. So what ends up happening? The reaction goes through and says, well, I have too much product, so I'm going to take that product and I'm going to put it over here to balance it out. Okay. Once it has re-achieved equilibrium, if we go through and mess with it again by either taking some or putting some back on, it now needs to go through and readjust. That is what LeChatlier's principle is looking at. That is equilibrium. Same idea can happen with our two chambers. We've got our reactant and we've got our product chambers. When we start a reaction, how much products do we have?
They're equal.
When you start a reaction, how many products do you have? None. So what we do is fill up the reactant chamber. What happens when we start the reaction? We're now allowing products to form. What happens? Barrier's removed. What happens to the liquid level? It's going to drop down and fill up in the product until we have even layers all the way across. Back to LeChatlier, what happens if I now pause the reaction? So I'll drop my barrier back in, and now I'm going to add some reactant stuff to it. Now I say reaction go. Now what happens? The reactant concentration goes up, the product concentration goes down. So our equilibrium will always shift and change the direction to favor either reactants or products to push us to those particular positions. All right? We will pick up there on Thursday.